from this mixed community onto media such that you transfer only one microbe or isolate it from all the others so that you can establish your pure culture. To do that, you're going to need sterile instrumentation. This is where flaming your loop comes into play. You're going to need aseptic technique. This is where after you flamed your loop, you don't contaminate it by setting it on the table. And you're going to need the appropriate media in order to grow the microbes. When we were dealing with a mixed culture, we were going to use a solid medium to isolate those bacteria. A broth culture won't be successful in isolating them. We're going to streak them onto a solid medium. That will allow us to separate the bacteria. And what are we going to use? Well, we're going to use an agar-based medium and add nutrients to it. Now, the agar itself does not provide any nutrients. It's an algae extract. But what's great about agar is that very few bacteria are able to degrade it. Prior to the discovery of agar, some of the things that were used were gelatin, potato slices, to grow bacteria on potato slices. But a number of bacteria are able to break down gelatin or able to break down potato slices. So those weren't really effective in growing microbes. Agar, bacteria can't break it down. There's no nutrient value there, so they don't. So it serves as a great stabilizing source. It's not destroyed at high temps. We can autoclave it, 121 degrees Celsius, under 15 pounds pressure, and not degrade the molecule, not degrade agar. So it's not destroyed at high temperatures. But the other thing, and this is something you've already experienced, it's solid at 45 degrees. It melts at 95 degrees. So we have this wide working range, really, if you will. We can melt the agar at 95 degrees. Okay. Let it cool down to 55 degrees and add amino acids and other things that we might need. And then pour it and let it solidify. And then we can incubate it at 70 degrees and not worry about it melting. So it doesn't solidify until it cools down to 45 degrees, but once it's solid, we can now incubate it at higher temperatures without the fear of it melting. All the way up to 95 degrees. So it allows us to test for microbes that grow at very high temperatures. The one thing that we will want to keep in mind is that if we are working with agar on a petri dish, this is not an airtight environment, and so the agar will dry out. One of the reasons we can't leave our plates in an incubator for an extended period of time is because you're at elevated temperatures. That would dry out the media and end up, eventually causing the death of the microbes. So, not an airtight system. The agar will dry out. Usually in about 2 weeks is the max that you can use a plate. Now slants and stuff like that, because we can tighten that cap down, those now can be stored for longer periods of time because they're not going to dry out. So let's talk about how bacteria grow in a laboratory. Let's look at the bacterial growth curve. Okay, now this is how bacteria grow in a laboratory setting. And this is very different than how bacteria grow in the environment. In the environment, you're talking about a dynamic system in which things come into the system and things go out of the system. Energy comes into the system, waste can be taken out of the system, and you've got competition. In a in a laboratory setting, your system is closed. It's what's called a batch system, and so the nutrients are not increased. There's no nutrients coming in, so they'll be depleted, and there's no waste being removed. And so that will accumulate. And both of those will affect the microbe's growth. So, number of cells over here. So this is the relative growth. And this is going to be time down here. When you transfer bacteria to a new medium, like many of you have done today when you did your single colony isolation, when you transfer those bacteria to that new medium, it takes them a while. There's a lag time before we see any growth. What's going on during this lag period is that the cells are tooling up to grow. Okay, they've got to figure out what resources are available to them. What's the sugar that I have available to me? What proteins do I need to break that sugar down? Yada, yada, yada. So they're making the appropriate proteins that they need for growth during this lag phase. Once they've done that, then we see that the bacteria generation time or doubling time takes off, becomes exponential. We call this the logarithmic phase or the exponential phase. And here, the microbe is growing at its fastest rate. The doubling time is at its fastest during this phase of growth. This is when we want to test bacteria for different things. This is when we want to test them for their gram character. This is when we want to test them to see what effect drugs might have on them. However, as we continue to grow, we are using the nutrients that are in the media. So now the nutrients start to become depleted and our waste is starting to accumulate, right? And so our growth starts to level off. This is a stationary phase in the growth curve. And a stationary phase, the birth rate and the death rate are the same. So the new cells that are forming are equal to the cells that are dying. Up until a point, then we see that there is a rapid die-off. This is the death phase. We've reached a point now where there's just too much waste and there's not enough nutrients to support the cells that are there, and so you see this logarithmic decline, this constant decline, if you will, not to the degree that we saw the doubling of the culture, or the growth of the culture. And at some point, the cells that are dying become a fuel source for the cells that are still alive. And so eventually you get this very prolonged death phase in which cells here are surviving off of the dead cells in the colony. Are still alive or will be born soon, yeah.
Does it ever disappear, like those whole bacteria die out?
Yeah. This cannot go on indefinitely. So at some point, yeah, because there's no new energy coming in, And because you have no new energy coming in, eventually, law of thermodynamics, it's all going to be gone. And so, yeah, this will eventually die. Depends on the microbe. You know, those that form endospores, you might be able to recover cells from this colony later on. But those that don't form endospores, probably, you know, it's hard to say. Each microbe is different. They're going to live longer or shorter depending on their behavior. But yeah, at some point, all the cells will be dead.
So if they have more nutrients than this prolonged graph can go up again, so it's exponential?
Well, how are you going to add more nutrients, though? Because we're talking about growth on an agar plate, okay? And there's just no way that you can put more nutrients in it. So this is a growth phase for a closed system or batch system, and this is the order that we see with all microbes, all bacteria behave this way in a laboratory setting. Here's something scary. So do we. If you think about it, we are right here. I don't know where we are on this exponential growth, but the human population is growing exponentially. I mean, we're growing like crazy right now. You got to figure at some point, unless we move to another planet, get transplanted, we're going to run out of either resources or our waste is going to accumulate to the point that we become stationary. And then do we fall into a death phase and then a prolonged death? You know, probably not. We'll blow ourselves up before we get there. But yeah, this is the pattern that you'll see for every microbe. Once you transfer it to an agar plate or put it into a broth culture, this is what you're going to get. Another good essay question. Okay.
The prolonged is just prolonged, not prolonged death.
Prolonged death phase. Yeah, prolonged death phase. Well, let's take a moment now and consider the environmental factors that will influence growth. We can start by talking about temperature. Each species, each microbe species has